Okay? E1 is the matrix that multiplies the first row by 1/3. Now, if you multiply the first row of a matrix by 1/3, what do you have to do to undo that? Well, you multiply it by first row by 3. If I take any matrix, multiply the first row by 1/3, and then take the matrix I get and multiply the first row by 3, I'm back where I started. Well, we do that to the identity matrix. Multiply the first row of the identity matrix by 3, and here we have it. And you can verify. You can multiply this by this, and it's very clear that you get the identity. And if it isn't, write this and this, do the multiplication. Then write it in the opposite order. Write this one on the left, this one on the right, and do the multiplication. It doesn't matter. These are inverses. And again, we just do the inverse operation to the identity. The operation was multiply the first row by 1/3. Here, multiply the first row by 3. That would undo multiplication by 1/3. In the second row, we add 5 times the first row to the second, remember? So how would, if we have any old matrix, take 5 times the first row, add it to the second, replacing the second. Well then, I'm not sure I said that right, so I'm going to say it again. Multiply -5 times the first row, add it to the second, and replace the second. Okay? So, to undo that, we multiply the first row by 5 of our new matrix and add it to the second, and that's going to get us back to where we started. So there's the inverse of this matrix. Now there's one type of matrix I didn't use. It's where you switch 2 rows. Well, if you switch rows 1 and 3 of a matrix, and then take the resulting matrix and switch rows 1 and 3, you're back where you started from. So, yeah, you would switch rows 1 and 3 of the identity matrix, which has to have a bigger matrix, at least a 3 by 3. Okay, well, that's how you get the inverse matrices, the inverse elementary matrices. It's very, very simple. Just got to practice it a little bit and think about what it means. So it's going to be very easy to get your lower triangular matrix, E1 inverse, E2 inverse. Now, I didn't actually do that for these matrices, but you should think about just doing the calculation and completing it. Okay, well, now E1 inverse and E2 inverse are both lower triangular, so their product is lower triangular. I think I might have, I said it before, but we hadn't seen E1 inverse and E2 inverse, and we hadn't seen that they are lower triangular at that point. But they are, so their product is lower triangular. So A equals LU, L equals E inverse, E1 inverse, E2 inverse. Okay. Now, what worldly good is that to us? Well, it turns out different large matrices in general, this is an extremely efficient scheme. The LU decomposition is an extremely efficient scheme for solving a matrix equation, okay, with the form AX equals B. Now for a 2 by 2 matrix, there are many more efficient ways to do it. For a 20 by 20 matrix, LU decomposition is actually, although it takes quite a number of calculations, it doesn't take that many. Compared to other methods, okay, to brute force methods. So, take my word for it, this is really kind of a big deal. It's kind of important, and you're getting the idea of efficiency of a calculation, which is a very important idea, as long as, once we get quantum computers, maybe it'll be less important. But it's not clear that we're going to get them, although it's promising. And working with the computers that we have, efficiency in analysis is still very important. There's mountains of data to be analyzed. You do most of it with matrices, and LU decomposition is an important technique.